So what we're going to look through here is, given a function, how can we use properties of that function along with properties of the derivative to get a really good sketch going of graphing the function without just plotting points, without going to a graphing calculator. So what we have right here is a polynomial function, and we'll get a little bit of review of just looking at this and seeing what this means about polynomials as well. But let's go ahead and start working through these. So recognizing that this is a polynomial, our domain should be all real numbers. Negative infinity to positive infinity. We can plug in absolutely any value for x, and we can get a number out for f of x. Okay, critical numbers of f. So what we're doing here is looking for where is our first derivative equal to 0. So let's go ahead and take our first derivative. We are going to have product rule here. So let's go ahead with the derivative of the first. So I'm going to have this -1 just kind of hanging out. Derivative of x minus 1 is just a +1, and then we keep the x plus 3 cubed. And I'm going to go plus that -1, so I'm going to go minus there just for plus the negative, and we'll have the x minus 1. And then derivative of x plus 3 cubed, we're going to have chain rule, so we're going to have times, bring the 3 down, x plus 3, bump down the 3 to a 2. Derivative of x plus 3 is just 1. And then let's make this look a little pretty. So we'll have a negative x plus 3 quantity cubed minus 3 times x minus 1 times x plus 3 squared. And we want to see where this is equal to 0. What I'm going to do is I'm going to go ahead and factor out a negative and then an x plus 3 quantity squared. So what this will leave me with is I'll have just a single x plus 3 left. Factoring out that negative will bring this back to a positive. And then we'll have 3 times x minus 1, so 3x minus 3. Okay, so 0 equals negative x plus 3 quantity squared, and then we'll have 4x. And what this means then is if that equals 0, so we'll have a negative 4x equals 0, which means we're getting an x equals 0 as a critical point. And then we also have x plus 3 equals 0, so an x equals -3 as a critical point. And if we want the actual coordinates, what we could do is, now we know the x values of 0 and -3 are critical. And then to get the y coordinates, what we do is go and plug into our original function. So if I plug in 0, let's see, that would be a -1 and then a 3 cubed. So it looks like a +27. And then if I plug in a -3, we will get out, let's see, -4 times 0. That's going to be a 0. So there's our critical values, critical points. Let's build a table for increasing, decreasing. So that 0 and -3 is going to split up my intervals here. So we're going to go from -infinity to -3, -3 to 0, and 0 to infinity. And I'm going to evaluate the first derivative for a number in each of these intervals. Just choosing a random number that fits. And then we're going to plug this into our first derivative. So if I take the first derivative with the -4, let's see, that'll be a +16. That x plus 3 squared is always going to be positive. So really I'm just focused on that -4 times the value that I input. So that's going to be positive for +16, increasing. If I plug in a -1, that's also going to be positive for increasing. And if I plug in a +1, it'll end up negative, so we'll be decreasing. So this gives me an idea of the trends that we'll have as we go across the function. And also what I can see is if we're increasing, then increasing, I'm thinking that -3 might be an inflection point because the trend stays the same, but we can confirm that when we go to our second derivative. And then going from increasing to decreasing, I'm seeing that at that 0, that's likely going to be a local maximum, just from our first derivative test. Okay, if our first derivative, once we got it all simplified, was that -4x times x plus 3 squared, let's go ahead and take the second derivative. So product rule again, so -4 times x plus 3 quantity squared plus -4x, so let's go minus 4x, and then drop down the 2, x plus 3 to a positive 1, times the derivative of x plus 3, which is just a positive 1. And then we'll just simplify a bit. Looks like I can factor out a -4 along with an x plus 3. And that'll leave me with, we'll still have an x plus 3 in that first term. We'll have plus 2x. So we're looking for where our second derivative is equal to 0, and we have a -4 times x plus 3 times 3x plus 3. So x plus 3 equals 0, x equals -3, which confirms what we were thinking up here with that inflection point being at -3. We also get an inflection point at -1. And if we want that actual coordinate, so we know we have the coordinate -3, 0 from what we found up above. If we plug in -1, let's see, that would be a negative times -2, so positive 2 times 2 cubed. So that'll be a positive 8. Positive 16, 2 times 2 cubed. So 2 to the 4th power. Okay, there we go. All right, build a concavity table. So we're going to have cutoffs at -3 and -1. So -infinity to -3, -3 to -1, and -1 to infinity. And let's look at our second derivative at coordinates in here. Okay, so if I plug in a -4, that will be negative. So we have concave down. And then if we plug in -2, that should come up to a positive value. So this is concave up. And then for our second derivative at 0, that should end up being negative. So that'll be concave down. Okay, list any local minimums, local maximums, and inflection points. So we found that local maximum at 0.27. We have an inflection point at 2 spots. We have the -3, 0 and -1, 16. Find the vertical intercept and any horizontal intercepts that exist. So this is just going to use our original function. So our negative x minus 1 times x plus 3 cubed. So vertical intercept is just about plugging in x equals 0, which we already have. So we know that comes out to 27. So there's our vertical intercept is 0.27 because we already did that work. For the horizontal intercepts, this is where we go 0 equals negative x minus 1 times x plus 3 cubed, which means we'll have an x minus 1 equals 0, an x plus 3 equals 0, so an x equals positive 1, and an x equals negative 3. Okay, let's grab all of this information and start making a graph. So I know I need to see up to 27 along the y-axis, so what I'm going to do here is use increments of 3, and then I'm going to do increments of 1 along the x-axis. So we have 0.27, so 1, 2, 3, 4, 5, 6, 7, 8, 9. we have a -1, 6, or let's go -3, 0. And let's also grab that 1, 0. And then we have a -1, 16. So 2, 3, 4, 5 for 15. And then just one more. And I think that's what we have in terms of coordinates. Now, something that we have too is an idea of concavity. So to the left of -3, and I can even think of it as these kind of different segments here. I'm just going to put these lines temporarily. And let's actually start with increasing, decreasing. So if we go to our increasing, decreasing table, what we saw is that we have increasing, then we're still increasing, and then we're decreasing. So I'm thinking is that we're going up, up, and then down. So I should have that. Then inflection points. So inflection points were both at -3 and -1, so we also have inflection here. And what it told us on our table is that it's going to be concave down, and then we'll have concave up, and then we'll have concave down. So what we need is some sort of downward curvature here, but still increasing. Then we need to switch to increasing but concave up, so curving upwards. And then we're going to switch to concave down as we hit that maximum and go down. And that gives me a really good shape for what we're dealing with here. So concave down and increasing. I don't want to quite do that. Then we're going to level out for our inflection point so that we can switch to concave up. And then here we're switching to concave down, but still increasing to reach that peak for that local maximum at 0.27. And then we're decreasing down and still keeping that concave down curvature. All of that gives us a really good shape for our graph. And then after we do all of that work, go ahead and confirm it. Make sure it matches with what we would have here. So f of x equals -x minus 1 times x plus 3 cubed. And there we go. Matches almost perfectly. So with this, and in pre-calculus, we do a lot of practice of curve sketching with polynomials, but it's hard to get this idea of the curvature that's coming through and how the concavity changes and where the increasing, decreasing changes. But now that we have calculus, we can find those critical points, find those inflection points for exactly where they're switching. And it just makes for such a better picture of making a sketch of a graph.